In the third exercise of this session, we are asked to write a custom user mode exception handler. And all this exception handler has to do is jump over the faulting instruction. So a relatively simple exercise, but you need to know how to work with these control status registers. We explicitly refer to these tables at the bottom of the exercise assignment to see how you should do this. If you've watched the presentation, you should also know how this works. So, first of all, the first line of code here, we set our use status to 1. Why? Well, this enables interrupts, and this is specifically required in RARs at the time I record this video to enable interrupts. Currently, we have a pull request going to modify RARs to not have this requirement anymore, because to us it makes little sense. But for now, if you want to write a custom exception handler, you need to write this value 1 to the interrupt enable in the use status. So next, and this is of course important, next we load the address of our custom handler to T0, and then we write this T0 value to UTVec. So the CSR-RW instruction, how does it work? Let's see. So read from the CSR into T0 and write T1 into the CSR. So T1 is written into the CSR, CSR is written into T0. So UTVec, uStatus, uScratch, UEPC, those are all CSR register, control status registers, special registers used, for example, in operating system implementations, in trap handling. These are not meant to be used as regular registers. These are special registers for trap handling, for example. The control status registers, and using these instructions, we can access them. So, as we know, or if you might remember, in UTVec, we expect the address of our custom trap handler. Whenever an exception occurs that is delegated to user mode, in that case, the UTVec location, that's where we will jump to. That's where the RISC processor will find your exception handler. So we wrote a custom handler, we have to write the address to UTVec. And that causes the next exceptions that will be delegated to user mode to be handled by this handler. So this delegation to user mode, as mentioned in RARs, we did this by setting this use status to 1. In RISC, this happens by setting ME delegation registers and optionally SE deleg, and you can use those as seen in the video to forward exceptions to user mode, specific exceptions. In this case, once we set interrupt enable to 1, all of the exceptions are forwarded to user mode. Well, not all, not the eagles. In any case, we now trigger a trap. So this line here, let me first demonstrate real quick what would happen if I comment out these first 3 lines and execute my program. I get immediately a runtime exception at this address, and it's marked here. This instruction faults when I execute it. It causes an exception. And if we don't enable interrupts and define our own custom exception handler, RARs just stops when it encounters an exception and displays what the exception was. And what it sets is load address not aligned to word boundary. Why is this? Because whenever we use the load word instruction in RISC-V, the address that you provide must be a multiple of 4. It must be aligned to a word boundary. In this case, this is not the case, so this instruction raises an exception. It triggers a trap. So this instruction should cause the PC to jump to here, the beginning of our custom handler, because it looked at the value in UTVec, and then our handler is executed. Now let's see how we actually wrote our exception handler. So for an exception handler, it's important that you don't overwrite any registers. Why? Well, these exceptions could in theory occur at any point in a user's program if they made some mistake somewhere, for example. And in this case, it would be very unfortunate if the exception handler overwrote registers that the user program was using. So you want to make sure this handler doesn't touch any of the user registers. It simply, if it needs to use them, which it probably will need to use some register, in that case, we need to back those registers up and restore them at the end. And for this purpose, exception handlers have a useScratch register. And this register you can just use for any type of value as a scratch register, as a throwaway register, as a temporary register. And so what we do is we move in the beginning of our exception handler the value of t0 to useScratch. This backs up t0 in useScratch, and this makes it so that we can freely use t0 now to do anything we want. The purpose of our exception handler from the assignment was to simply ignore the exception and to jump over the faulting instruction. So we just want to do nothing but jump over the faulting instruction. Now, the address of the faulting instructions in UEPC and the address after the faulting instruction, that's UEPC plus 4. So that's what we do. We first load the value of UEPC into T0. Meanwhile, we write 0 to UEPC, just as a temporary value. We add 4 to this value because UEPC currently is pointing to this instruction. Then we write this value increased by 4 back to UEPC. So now UEPC is pointing to this line of code, the line after our faulting instruction. And then finally, before we actually return for our trap handler, we have to restore the value in T0. And this was written to useScratch. So we write useScratch to T0. We write 0 to useScratch. And then we execute the user return instruction, the uret. This is how you return from an exception handler with uret. And this causes us to jump to the control status register UEPC. And this is currently pointing to this value, load immediate A710, which is the exit 10 system call that is finally executed. So if we execute this program, instead of getting this runtime exception, this instruction is just ignored. And as we can see, the program, let me clear, let me run again, the program has just finished running with status code 0. So we wrote a simple exception handler, doesn't modify any values. The value of T0 was untouched, so if we look at it, it should have the address of our handler, in fact, and that should be correct. If I display this as a hexadecimal, T0 still contains indeed the address of our code handler, because that's what we loaded here. And even though we did calculations here with T0, we restored it from useScratch and it has remained untouched. So it's basically as if this instruction never happened, and the program would execute exactly the same if we just commented this line of code and ran. There is no difference. That's the point of this simple trap handler. Ignore the mistake and jump over it.